Welcome to Module 8 of the course on application of spectroscopic methods in molecular structure determination. In this module, we will consider carbon-13 NMR spectroscopy. Just like proton NMR spectroscopy, carbon-13 NMR spectroscopy is also a very valuable tool in structure elucidation problem. Now, as far as carbon isotopes are concerned, carbon-12 isotope has no spin. In other words, it is spin inactive. I is equal to 0. Whereas carbon-13 nucleus has a spin of half, just like proton has a spin of half. Therefore, carbon-13 NMR spectroscopy is possible, and it is a very useful tool in organic structure elucidation because it gives a lot of information about the carbon skeleton of the organic compounds. Now, this table gives some important properties of the carbon-13 isotope of carbon. Carbon-13 isotope is low abundant nucleus. It is only about 1.1% of the carbon content that is available on Earth's crust. The nuclear spin is half, just like proton. The gyromagnetic ratio is just about 1/4 of the gyromagnetic ratio of proton. Proton gyromagnetic ratio is somewhere around 24 something. It doesn't have any quadrupole moment. The gyromagnetic ratio being 1/4 of proton, the resonating frequency is also about 1/4 of the proton resonance frequency. In other words, if the proton resonance frequency is 500 megahertz radio frequency, then the carbon-13 under the same magnetic field strength of about 11.7 Tesla, the carbon will resonate at 125 megahertz or so. There are several practical problems associated with the poor sensitivity of carbon-13 NMR. First of all, it is a low abundant nucleus. It is only about 1.1% of the total content of carbon or the Earth crust is NMR active. The rest is not NMR active, namely carbon-12. The gyromagnetic ratio is also low. It is about 1/4 of the proton gyromagnetic ratio. Both these factors are responsible for the poor sensitivity of carbon. Therefore, carbon-13 spectroscopy is only about 1 in 6,400 of the proton NMR spectroscopy. In other words, it is about 1.5 10 to the power minus 4 times less sensitive than proton NMR spectroscopy. For this reason, that is the poor sensitivity of carbon and other similar nuclei which are low abundant and low gyromagnetic ratio, there was a necessity to develop a new technique called the Fourier Transform NMR technique. There are two types of NMR spectrometers available. One is a continuous wave NMR spectrometer. This is of course no longer in use. Continuous wave NMR spectrometer was the original development of NMR spectroscopy. Later on, the Fourier Transform NMR spectrometer was developed. All the modern spectrometers are Fourier Transform NMR spectrometers. Now, in the continuous wave NMR spectrometer, the magnetic field is scanned and the radio frequency is kept constant in bringing each nuclei to resonance one at a time. In other words, signals are recorded one at a time by scanning the magnetic field, keeping the radio frequency constant. That is why we say 60 megahertz NMR essentially means the operating frequency is 60 megahertz and the magnetic field strength is varied to cover certain spectral scan widths. The continuous wave spectrometer process is a fairly time-consuming process because each scan has to be accumulated and averaged. On the other hand, in the FT technique, a very short pulse of radio frequency covering a range of frequency is applied, and this brings all the nuclei to the resonance simultaneously. The nuclei are then allowed to relax to ground state, and the resulting free induction decay is Fourier transformed. This is pictorially represented here. This is the free induction decay of a single nucleus, for example. It is a sinusoidal decaying curve is what is shown here. This is the signal intensity versus time. Over a period of time, the nuclei relaxes back to the ground state, indicating the free induction decay of the signal as it is shown in this picture. This is for a single frequency. If multiple frequencies are involved, then one gets a beat pattern like this, involving, let us say, for example, in this case, 4 different frequency with the high frequency in the blue and the low frequency in the magenta color that is shown here. And the time averaged spectrum, the time domain spectrum looks something like this with a free induction decay. And when it is Fourier transformed, the individual frequencies are sorted out, and the process of sorting out the time domain spectrum into a frequency domain spectrum is what is known as the Fourier transformation. The advantage of the FTNMR technique is that it is possible to bring all the nuclei into resonance simultaneously. This saves time. Accumulation of signal is possible by repeated scans and signal averaging in a fast way. This results in a better signal to noise ratio. This diagram essentially shows the effect of the number of scans on the signal to noise ratio. You can see here this is a single scan spectrum. This is an average of 4 scans, and this is an average of 16 scans. So you can see in the baseline this is fairly noisy. The signal to noise ratio is 18:1. This is relatively better. The signal to noise ratio is 34:1, whereas this is the best spectrum among the three in terms of this noise being very low. The signal to noise ratio is about 71:1. This essentially shows that the more number of scans that one averages, the signal gets better. Noise is random, so it gets cancelled out in the averaging process. So as a result of that, you get a better signal to noise ratio by averaging the spectrum with a long number of scans. The carbon-13 spectrum is usually recorded under the conditions of proton decoupling. In other words, a separate proton frequency is applied, and all the information about the carbon-13 proton coupling is decoupled by irradiation or saturation of all the protons. This is something like a double irradiation experiment, except it is a heteronuclear double irradiation experiment. Both carbon-13 and proton are simultaneously irradiated. Carbon-13 spectrum is observed and proton is decoupled. Therefore, each of the carbon appears as a single line in the NMR spectrum. Therefore, only a single line is observed for each chemically different carbon in a carbon skeleton of an organic compound. Now, from the symmetry of the structure, one can easily predict the number of signals to be expected for a compound. An unsymmetrical chiral compound like this one, for example, which contains 7 carbons, all the 7 carbons are chemically different, therefore one gets 7 signals for this type of a compound. On the other hand, a highly symmetrical compound like benzene, which has a D6H symmetry, all the carbons are equal and chemically identical, therefore only one signal is obtained for all the 6 carbons. This is another example of a steroidal kind of a skeleton with 17 carbons on the skeleton. All the 17 carbons are chemically non-identical, they are chemically different, so 17 signals will be observed for this kind of a compound. Take this example. This is called superphane, where 2 benzene rings are connected by a ethylene bridge in all the 6 carbons around it. This benzene and this benzene are parallel to each other in more or less, and this is a highly symmetrical structure. There are only 2 types of carbon. One is the aromatic carbon. All the 12 aromatic carbons, namely the 6 of this benzene ring and 6 of this aromatic ring, are identical. So it gets one signal for the aromatic carbons, and all the side chain carbons are also identical. All the 12 side chain carbons also give only one signal. So this is an example of a highly symmetrical molecule, fairly complex molecule, but a highly symmetry nature of this molecule essentially leads to only 2 carbon signals. One can easily distinguish the ortho isomer from the meta and para isomer by carbon-13 spectroscopy. When the 2 substituents are identical, as in the case of, for example, orthoxylene, metaxylene and paraxylene as it is represented here, this gives 4 signals. Essentially, for the 2 methyl groups are identical, so it gives 1 signal. These 2 carbons are identical, so 1 signal. These 2 carbons are identical, and these 2 carbons are also identical. So it is essentially 1, 2, 3, 4 because of the plane of symmetry that passes through this particular carbon-carbon bond and this carbon-carbon bond. Here also there is a plane of symmetry. The plane of symmetry passes through this carbon and this particular carbon. So there is carbon 1, carbon 2, carbon 3, carbon 4 and carbon 5. There will be 5 distinct signals for 5 different carbons in this molecule. On the other hand, this has a molecular symmetry, plane of symmetry in this direction as well as in this direction. So there are only 2 types of ring carbons, the ipso carbon and the ortho carbon. So this gives 2 signal and the methyl gives a 3rd signal. So there are totally 3 signals observed for the paraxylene molecule. So this essentially tells us that the more the symmetrical the structure is, the lesser number of carbon signals that one would obtain in an NMR spectrum. The highly unsymmetrical structures will lead to maximum number of signals in the NMR spectrum. The difference between the Proton NMR and the Carbon-13 NMR, which is very crucial for structural elucidation, is this particular point. In the Proton NMR spectrum, one does not get a signal for any of the groups, just like internal acetylene, tetrasubstituted olefin, cyanofunctional group, carbonyl functional group, and quaternary carbons. Now these carbons do not bear a proton, so there is no proton signature in the Proton NMR spectrum for any of these groups. On the other hand, in the Carbon-13 spectrum, one gets a direct evidence for groups like acetylenic carbon, cyano, carbonyl carbon, quaternary carbon, and so on. So these are easily detected in the Carbon-13 spectroscopy in comparison to Proton NMR spectroscopy, where one does not get a direct evidence for the presence of any of these groups. Carbon-13 spectrum is normally acquired on the broadband decoupling mode. In the broadband decoupling mode, Carbon-13 spectra are recorded simultaneously with the saturation of the proton spins using a second radio frequency corresponding to the proton. This results in the complete decoupling of the protons, and only carbon peaks are seen in the spectrum, and the CH information, coupling information, is completely lost or absent in the process. This is an example of a Carbon-13 spectrum, which is a broadband decoupled Carbon-13 spectrum of this particular diester. You can see here the carbonyl carbon comes around 169 or 68 ppm. The ipsocarbon as well as the orthocarbon, namely carbon number 2 and carbon number 3, they accidentally merge in the spectrum. They come at the same frequency. This is fairly common in Carbon-13 spectroscopy because a narrow region where the aromatic carbons come, some of them can be merging on top of each other. Then carbon number 4 comes around 61 or 62 ppm. Carbon number 5, which is the terminal methyl, comes around 15 ppm or so. So from the number of signals that is expected and the number of signals that one sees, one can sort of arrive at the molecular structure to be the para-disubstituted derivative in this particular case. This particular spectrum illustrates the point that the cyano-functional group and the carbonyl functional group can be detected in the Carbon-13 spectroscopy. Remember, we solved the structure of this particular compound using Proton NMR spectroscopy and got an indirect evidence that there is a cyano group based on the unsaturation index as well as the chemical shift values of this particular proton, which is an indirect evidence that the cyano group is attached to the carbon in this particular molecule. On the other hand, in the Carbon-13 spectroscopy, you get a direct evidence for the cyano-functional group as well as for the carbonyl functional group in this molecule. The second methodology that is used in the Carbon-13 spectroscopy is called the gated decoupling. We will deal with the gated decoupling and the off-resonance spectroscopy in much more detail in another module. For the time being, all you need to know is that the decoupler is switched on during the delay time and it is off during the data acquisition. In other words, the Carbon-13 spectrum is completely proton coupled. It also has the advantage of the nuclear Overhauser effect enhancement. We will see about the nuclear Overhauser effect in much more detail in another module. For the time being, this information is presented essentially for completion. Now, if you look at this spectrum, this is a completely proton decoupled spectrum of menthol. Menthol is this particular molecule. And if you look at the number of carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 signals are there. So it must contain 10 carbons, 6 ring carbons, and 1 isopropyl 3 carbons are there, and another methyl group 1 carbon. So totally 10 carbons are there in this particular molecule. It's a completely unsymmetrical molecule. It is a chiral molecule. So one of the reasons all the carbons show up separately. The bottom spectrum is actually a proton coupled spectrum where the CH coupling information is retained and the spectrum is recorded. This is the gated decoupled spectrum and this is the broadband decoupled spectrum. In the broadband decoupled spectrum, all the carbon-hydrogen coupling information is lost, whereas in the gated decoupled spectrum, all the carbon-hydrogen information is present, coupling information is present. One can analyze the spectrum, although it is a fairly complex spectrum. It is possible to analyze the spectrum and obtain the carbon-hydrogen individual coupling constants from the spectrum. Here is another example of a gated decoupled spectrum. This is a spectrum of glucose, for example, and this is a completely proton decoupled spectrum in the bottom trace. In the top trace you can see it's a carbon hydrogen coupled spectrum. When a carbon signal is split into a triplet, as in the case of the CH2OH, for example, you can see the intensity of the signal goes down considerably because this intensity is split essentially into triplet, so the intensity of each of these peaks in the triplet is much lower than the intensity that one sees in the bottom spectrum. Another technique that is used in the carbon-13 spectroscopy is the off-resonance decoupling. The decoupling frequency of the proton is not exactly matched, but it is offset by a few hundred hertz. Therefore, only the splitting information due to the protons that are directly attached to the carbon are seen here. In other words, when you have a methyl group, for example, it will be seen as a quartet in the off-resonance spectrum. A CH2 group will be seen as a triplet because the two hydrogens will split the carbon signal into a triplet. The CH kind of carbon, like say for example aromatic carbons, unsubstituted aromatic carbons bearing a hydrogen, would appear as a doublet. Quaternary carbons, of course, don't have any hydrogen to split, therefore that will appear only as a singlet. So from the multiplicity one can identify whether it is a CH3 carbon or a CH2 carbon or a CH carbon or a quaternary carbon using the off-resonance technique. And the off-resonance spectrum is presented here for the vinyl acetate. This is a vinyl acetate spectrum. This is completely proton decoupled spectrum. There are 4 carbons and the 4 signals are seen. The one for the carbonyl signal, the other one for the internal alkene carbon. The terminal alkene carbons comes separately, and finally the methyl carbon also comes separately. So the methyl carbon now in the off-resonance spectrum appears as a quartet, whereas the CH2, the terminal carbon bearing 2 hydrogens, appears as a triplet, although the triplet is a highly distorted triplet, not a regular triplet, and the CH carbon of the olefin appears as a doublet because there is one carbon attached. Finally, the carbonyl carbon, which does not bear any kind of a hydrogen, appears as a singlet both in the decoupled spectrum as well as in the off-resonance spectrum. Now, unlike the proton NMR signals which can be integrated, the intensities can be quantified. Carbon-13 spectrum is usually not quantitative. One does not measure quantitative carbon-13 NMR spectrum. There are 2 reasons for it. Because carbon nuclei have much longer relaxation time, so it takes a long time for them to come back to the ground state before the second pulse is being applied. So sometimes the signals get saturated inadvertently. In addition to that, the nuclear over-exposure effect also plays a role. Different carbons have different amount of nuclear over-exposure effect or the enhancement due to the nuclear over-exposure effect. So because of these 2 reasons, the signal intensities are not proportional to the number of carbons that are present under the different chemical environment. There are 2 relaxation mechanisms by which the excited carbon spin comes to the ground state. One is by spin lattice relaxation or the longitudinal relaxation, and it is designated, the relaxation time is given the symbol T1, and the relaxation essentially takes place by the dispersion of energy to the surroundings, which is the lattice. It could be solvent or the surroundings. The alternative mechanism for the relaxation process is the spin-spin relaxation or the transverse relaxation. In this particular relaxation process, the relaxation is by dispersion of the excess energy of the spin to other active spin nucleuses present in the molecule. In other words, for example, if the carbon were to relax, it can pass on the energy to another spin active nucleus like fluorine, phosphorus or hydrogen, and thereby it comes back to the ground state by a spin-spin relaxation process. Now we will deal with the nuclear over-exposure effect in a much more detailed manner in another module. For the time being, let us just define what is the nuclear over-exposure effect. The enhancement of signal intensity due to heteronuclear decoupling is what is known as the nuclear over-exposure effect. For example, the carbon-13 signal intensities are enhanced due to the irradiation or the decoupling of the protons, because the population distribution is different under the conditions of proton irradiation compared to under the conditions of only proton not being irradiated. This is because the major relaxation route involves the dipolar transfer of the excited state energy to the proton, which are directly attached to it. In other words, the transverse relaxation is what is responsible for the enhancement process that takes place. Therefore, NOE will be maximum for the carbon which has maximum number of hydrogen, namely CH3, and then CH2 and CH in terms of intensity. So therefore, the peak intensity will be normally CH3s will be more intense, CH2 will be the next intense line, CH also will be next intense line. Finally, the quaternary carbons will have the least intensity. One can easily identify quaternary carbons in a carbon-13 spectroscopy because of the poor intensity of that signal compared to the other signals. In order to relax the carbon-13 nucleus back to the ground state, there is a technique that is available wherein a paramagnetic relaxation agent such as the chromium acetyl acetonate is added. It reduces the longitudinal relaxation period. In other words, it allows the carbon to nuclei to relax much faster. Therefore, faster signal averaging is possible. You don't have to wait for the pulses to be given with a long delay durations. Normally, about 10 to 100 millimolar relaxation agent is added, and the solution is taken a slight pink color because of the chromium acetyl acetonate being a slightly pink color in nature. The result is that signal intensities of the quaternary carbons are now very much enhanced. This is illustrated in this picture. This is a spectrum of camphor. This bottom spectrum is without the relaxation process. The top spectrum is with the relaxation agent, namely chromium ACAC being added. The two spectra are identical except the top spectrum is along with the chromium acetyl acetone, which is the relaxation agent. So you can see here the effect of the relaxation agent. This is the quaternary carbons. There are two quaternary carbons in this molecule. One is this bridgehead carbon. The other one is the bridging carbon itself is a quaternary carbon. Those two carbons appear as signals with low intensity. With the relaxation agent, of course, you can see that their signal intensity is much improved because the faster relaxation of the carbon which comes back to ground state and does not get saturated in the process. Now, the chemical shift range of a typical carbon-13 spectrum is from 0 ppm to about 220 ppm. Most of the carbons would resonate in this particular range of frequency from 0 ppm to about 220 ppm. And this chart essentially tells what kind of carbons has come and what kind of a chemical shift value. Starting from the higher end, if you look at the 220-200 region, it's mostly the carbonyl carbons come in the region. Carboxylic acid derivatives come in the region between 160 to 180 or 185 or so. The aromatic carbons come in the region between about 110 to about 140 or 150 depending upon whether you have electron donating substituents or electron withdrawing substituents. Those with electron donating substituents will be shielded, so they come in the region of 110 or 120, whereas those carbons bearing the electron withdrawing groups like the nitro and chloro and so on, they will come in the region between 130 and 140. Internal olefins carbons come in the region same as the aromatic region. In the case of proton NMR spectrum, the aromatic hydrogens come at a higher delta value compared to the olefinic hydrogen because of the ring current effect. In the case of carbon-13, such ring current effect is not possible because the carbons do not lie in the shielding or the de-shielding zone of the ring current effect that is normally seen. So the carbons are least affected by the ring current effect in the carbon-13 spectroscopy. Terminal alkynes come at a lower delta value. Cyano-functional groups are easily detected. They come in the region between 110 and 120 or 125 or so. The monosubstituted derivatives typically come between anywhere between 20 ppm to about 60 ppm depending upon the electronegativity of the group that is attached. The most electronegative group, for example, the fluorine attached one will come at around 80 or 90 ppm, whereas the least electronegative halogen, namely the carbon iodine bond, for example, that particular carbon comes even in the negative delta value because of the large size of the iodine which completely shields the carbon. So one has to familiarize this particular, one has to be familiar with this particular table or this particular chemical shift range of carbon-13 spectroscopy to be able to solve the structures of organic compounds. It's not necessary to memorize this, but it comes with practice what kind of a carbon will resonate at what kind of a frequency by solving more and more number of problems. Now, if you look at the spectrum of camphor, this is a proton NMR spectrum, just to show that the camphor is a completely unresolved spectrum except for these two methyl groups, the three methyl groups, methyl group A, B and C, which come separately. all the other hydrogens essentially appear as a bunch of unresolved signal in the proton NMR spectrum. On the other hand, if you look at the carbon-13 spectrum, each one of the carbon comes separately and it's a fairly well resolved spectrum. So in some sense, the carbon-13 spectrum is a much more resolved spectrum because of the fact that the individual carbons come at separate frequencies, and the spectral spread is also much higher, from 0 to 220 ppm, whereas proton is normally only from 0 to 10 ppm or 0 to 12 ppm or so. This is a spectrum which you have already seen. This is a spectrum of the diethyl phthalate. There are 5 different types of carbon in the molecule, and one sees 5 different kinds of signals in the NMR spectrum. Now when you reduce the symmetry to orthoester, in other words diethyl terephthalate, this one is a diethyl terephthalate, whereas this is diethyl phthalate. There is only one plane of symmetry in this molecule, so there are 6 possible signals that one can have. Carbonyl signal comes as the highest delta value, around 168 or so. Then comes the ipso carbon, which is carbon number 2. From the intensity itself, one can say that this is the ipso carbon because the carbon intensity is low. Carbon number 3 and 4, which are methane carbon, CH carbons, the intensity is much higher, and these are the 2 carbons which are 3 and 4, for example. And this particular carbon corresponds to the CH2, and this particular carbon corresponds to the CH3. If one records the off resonance spectrum, of course the multiplicity will tell which is CH2 and which is CH3. But for a simple molecule like this particular molecule, simple carbon-13 decoupled spectrum itself is an easily interpretable spectrum. Now if you observe carefully, there is a 3-line pattern which is coming around 77 ppm or so. This is around 77 or 76 ppm. This is because of the solvent peak. Remember, solvents also contain carbon, which contains carbon-13, so they would also appear in the case of carbon-13 spectroscopy. Unlike in the proton NMR spectroscopy, when you use a deuterated solvent, it will not show up in the proton NMR spectrum. But the carbon-13 spectrum will have signatures of the solvent peaks also. This is one such instance where the chloroform peak is seen here. Now this is CDCl3 peak is what is seen here. Essentially you see 3 lines with equal intensity because the deuterium couples with the carbon. The deuterium is not decoupled, only proton is decoupled. So the deuterium coupling essentially is deuterium being a spin 1 nucleus, the 2Ni plus 1 value corresponds to 3, and therefore the 3-line pattern is seen for the CDCl3. So just like the CDCl3 gives this particular spectrum, many other solvents also show up in the carbon-13 spectrum. It depends on whether it is a completely protonated cyclohexane 12 protons or cyclohexane per deuterated compound. In other words, you can have a deuterated solvent or a proteo solvent. The proteo chemical shifts are slightly different from the per deutero chemical shift value. These are the common solvents that one uses for carbon-13 spectroscopy, and the resonance frequencies of the per proteo as well as the per deutero solvent is given. Sometimes instead of using tetramethylsilane as an internal reference, the solvent peak is taken as a reference point, and with respect to the solvent peak, the rest of the spectrum is calibrated. Here is a spectrum of a diacetylene compound. This is a symmetrical compound with respect to the plane of symmetry passing through this particular carbon, bisecting this carbon-carbon bond. So you need to measure only half the number of carbons in the carbon-13 spectrum. You need to see only half the number. The 2 methyl groups appear as a singlet, as a signal here around 28 ppm or 26 ppm or so. The quaternary carbon, which is an aliphatic carbon, comes in this region of 45 or so. In carbon-13 spectroscopy, the more substituted the carbon is, the higher will be the delta value, and therefore this quaternary carbons comes here, and the methyl carbons, which are terminal carbons, comes at a lower delta value. The characteristic signature for these 2 acetylenic peaks are shown here. This is one acetylenic peak and this one is another acetylenic peak. From the intensity difference, one can tell this is the one which has the hydrogen, in other words the terminal carbon is this one, the internal acetylenic carbon is this one, and the lines that you see along with the acetylenic peaks are the lines due to the CDCl3 as a solvent here. Solvent peak is also shown. Now if you look at the aromatic region, there are 2 quaternary carbons. One can easily find out which are the quaternary carbons. One is here, the other one is here. Remember, acetylene has a shielding effect along its axis, so this particular carbon will be shielded and that comes around 121 ppm, whereas the terminal carbon would come at a much higher delta value, which is, sorry, the other two carbons, not the terminal carbon, the other two aromatic carbons would come at a higher delta value. This is one carbon and this is another carbon in terms of the two aromatic carbons, which are quaternary carbons. And finally, the three CH carbons of the aromatic also comes. From the intensity we can tell these are the CH carbon. Which one is which is rather difficult to say. One can calculate based on certain additivity rules as to find out what is the nature of this chemical shift of this for these three different CH carbons in this molecule. This is another compound, very similar structure, except this is a carbazole based structure and this is a fluorine based structure. This also has a plane of symmetry passing through nitrogen and bisecting the carbon-carbon bond here. A very similar spectrum is what is seen here. There are two acetylene peaks which are shown here, and the N-methyl peak is coming around 30 ppm or so. It's a substituted with a heteroatom. That is why it comes around 30 ppm. If it is substituted with oxygen, it would come around 60-65 ppm or so. Finally, you have the aromatic carbons, 6 carbons. All the 6 carbons are seen because the molecule does not, the aromatic ring does not have any kind of a symmetry. So as a result of that, all the 6 carbons show up separate peaks, out of which 3 of them are quaternary carbons and 3 of them are CH carbons, which are very clearly identified from the intensity profile of the spectrum. This particular molecule is a steroidal molecule. This is acetate of cholesterol. It has about 29 carbons or so, including the acetyl carbon. In fact, if one counts the number of signals that is given here, these are the frequency chemical shift values of the various signals that are here. You see about 27 or 29 peaks in this particular spectrum corresponding to the various peaks that can be obtained for this aliphatic compound. Now, the most de-shielded carbon is the carbonyl carbon of the acetate peak, and that comes around 170 or so. So that can be readily identified. And the olefinic carbons also, these are the olefinic carbons. There are only 2 olefinic carbons which show up in the olefinic region. The more substituted olefinic carbon coming at a higher delta value compared to the less substituted olefinic carbon which is coming at a lower delta value. And this is a CDCl3 peak, 3-line pattern that you see for the CDCl3. The rest of the carbons are all because of the skeleton that you have, which is basically an aliphatic skeleton. More or less a clean spectrum is what is obtained for the cholesterol acetate of this particular spectrum. So what we have seen is an introduction to carbon-13 spectroscopy in this, the various modes of accumulating the carbon-13 information. We had an introduction to the FT technique, namely the Fourier Transform NMR spectroscopy. Some examples of carbon-13 spectra are also seen in this particular module. In the problem solving session, we will deal with more examples of carbon-13 spectroscopy. Thank you very much.